Well, thank you so much for being here today. Our speaker, Dr. Desmond, PhD, is currently an associate professor at the University of Pennsylvania Paramount School of Medicine, where he directs the Center for Brain Imaging and Stimulation in the Department of Psychiatry. He also is an associate director of the Center for Neuromodulation in Depression and Stress, as well as the co-director of the Penn Brain STEM, Brain Science, Translation, Innovation, and Modulation Center. In addition to his appointment in psychiatry, Dr. Oss is also a secondary appointment in neuroscience, neurosurgery, neurology, and bioengineering at Penn. And if that would not make his schedule busy enough, he's also a licensed clinical psychologist and sees patients at the clinical practice at the Center for Treatment and Study of Anxiety. Dr. O's research uses structural and functional neuroimaging to understand causal connections in brain circuits and networks for the purpose of optimizing neuromodulation. He does exciting work on developing methods in interleaved concurrent TMS fMRI to advance and refine those techniques for clinical application. And of course, this exciting work is generously funded by institutional, private donor, and NIH funding and grants. And today we will hear about why fMRI guided TMS is or can be more effective for clinical conditions. Thank you so much for being here, Desmond, and we're excited to hear about your work.
Excellent. Will you guys be able to hear me through the Zoom if I'm this far away from the computer? Or should I rearrange?
It should be fine.
I think it's fine? Okay. Yeah, thanks for inviting me. I'm very happy to be here. And I should also say that there's one picture where there's a person in the scanner getting zapped, and it wasn't that long ago that we swapped it out for Ben Rosenberg's picture, who's in the corner there. Your picture used to be always in the slides until fairly recently. So Ben arrived at Penn before me to get all the IRBs written, set up all the equipment, and he's an amazing human being and scientist. So give him his proper shout out, even though his picture is not going to be in here. All right. So one of the issues with neuroimaging in psychiatry, there's a fairly substantial backlash that's been growing over the years of people saying, why are we even doing it? We've spent enormous amounts of taxpayer money on imaging in psychiatry, and it has yielded nothing, almost nothing that we can use clinically. And besides that, the imaging is noisy and has poor reliability, and you need thousands of patients before you can detect any reasonable association with behavior. So why are we even doing this? Here's another example. Even when we share data with each other and we have really massive databases, and you look across all these typical modalities of task, resting, diffusion, structural, it's really hard to find any reliable biomarker. And one of the challenges is that if you're an imaging person and you're used to looking at imaging averages, those average brains, think about translating that into an individual patient that walks through your door. It's not particularly useful because that's a conglomeration of many patients' data, and deciding that those imaging data are relevant to a particular patient is really challenging. Here's an example of how we usually report imaging data in studies, and that's on the left set of images. So this is a very typical cognitive task that's been run a million times in imaging studies, an N-back, and looking at the difference between a 2-back and a 0-back, looking for the difference in working memory load. You can make some really beautiful images that tend to pop up in the same places across people's studies. You're like, yeah, that's pretty basic cognitive neuroscience imaging protocol. right? And so the sets of images on the left are based on the average over a whole data set. And then on the right is something a little bit different, which I would argue is more relevant to individual patients. Instead of just looking at the average across all the people, the images on the right decided that they wanted a threshold based on the number of participants showing activation of at least some minimal amplitude in that voxel. So this one is more relevant to how many people in that cohort were actually showing activation in that actual spot. And you can see there's some overlaps, but there are differences. There's like a different hotspot, and a bunch of the activations go away. So where is the mismatch? It's because there could be relatively few subjects in the average brain with really strong activation in that voxel, whereas most of the participants may not have very strong activation in that voxel, and you still get the map on the left. And what we want for the individual patients is something more along the lens on the right side. So if we take this group map, throw it onto an individual patient's brain and just assume that that's where the networks are, it might be problematic. All right. Another problem that I think a lot of, especially data quant, like superstars, need reminding of is that our diagnoses aren't very good. So I'll give somebody a GAD diagnosis. I'll turn that same patient over to Ben, and he'll say, no, they don't have GAD. They're just sub threshold. They don't have GAD. And that's pretty reasonable. That happens a lot. And so to benchmark everything quantitatively on a diagnosis that is really pretty imperfect is problematic. So that's another reason why it's really hard to find a biomarker for depression. All right, but if you want something that could be a little bit better, the symptom data are a little bit more reliable. So if you're like, how bad is your worry, right? And I ask you, and Nicole asks you, then we're going to get pretty similar levels. So looking forward from that, keeping these caveats in mind, here's another parallel, interesting set of problems, which is that even when we get really amazing clinical effects from a brain stimulation protocol, like our friend Nolan at Stanford, this is amazing. This is so amazing, right? It's really helped all of us in the TMS world to say, look, what we do is super effective. TMS can be massively effective. Even when, right, these really brilliant new protocols come out, we're still treating the brain as a black box. We're still saying, okay, you should use image-guided targeting, and you should change everything in your whole stimulation protocol at the same time. And we don't know what's happening at the individual level in the patient's brain. And I would argue that could be super important, because even in the most amazing protocols, not all the patients do well. And we have no idea why. All right, we have this assumption that we're trying to guide stimulation towards this pathway, towards this target, but we really don't know how well that worked. Like, did it engage that target, or like why did we go? How did it go wrong with that patient? We're totally flying blind, and it's really hard to backtrack out of that. What to do with the patients who don't respond, especially. So one answer is, let's throw people into the scanner and see what actually happens in their brain when you stimulate that pathway, right? And this is very challenging technically, but we feel like it has some real utility to really understand what happens when an individual patient is stimulated, and how well it works, and how well the treatments work. So for people who are less familiar with functional MRI, one of its downsides is that it's pretty slow to get a signal. So if you have an event, you flash a checkboard, you have them press a button, something like that, and you want to capture the brain signature of that thing happening. It usually takes seconds before you start generating a really nice signal. And it's still related to the task. People don't care so much, in a lot of cases, that it's slow. So EEG is really fast, but you can't tell where in the brain it's happening. fMRI, you can tell where in the brain it's happening, but it's slow. right? So that's one of the downsides. Where that really helps us with TMS fMRI is that we can send a pulse of stimulation through a particular circuit, and we can capture the whole brain response to that pulse. So we can ping that brain circuit, ping when the scanner is not making an image, right? And then immediately turn on the image acquisition so we can capture the downstream brain response to that TMS pulse. So that's where if you did the RF pulsing at the same time as your TMS pulse, you corrupt the image, you get garbage. But given that you have this nice slow building effect, you can ping that circuit, you can capture the brain response to TMS pulses. When I say TMS pulses, I'm not talking about neuromodulation here. This is not repetitive TMS. These are single pulses. So it's sort of like getting a motor evoked response, right? You do a single pulse, you get a twitch. So we do that with the brain. We do a pulse and we capture the brain response. But if you're familiar with task fMRI, we do it the same way, which is that we have lots of trials, right? We have lots of trials of individual time points where we fire the stimulation, we capture the brain response, and then trials where there is no stimulation, so we get this background contrast, and then we average them over the whole fMRI run.
Can I interrupt you for a second?
Sure.
So do you have to couple up your stimulation with the scanner software, so you are interact? That's actually pretty pretty challenging.
So the easier version of integrating the scanner with the TMS is that you leave gaps in between your fMRI acquisition volume by volume. You leave little gaps in between, so you can do a TMS pulse in the gap. And TMS pulse is so fast that you don't corrupt the image as long as you have a gap. So you can have, we have 400 millisecond gaps, so they're pretty short. We've tested 200 millisecond, 600 milliseconds. So even with a 200 millisecond gap, you don't corrupt the image. So that's all you need. Build in that little gap, fire a little TMS pulse, and you can capture the brain response.
Not sure our MRI technicians would let us mess with the scanner software.
Also, there's an even more complicated version, which is the typical fMRI sequence does this kind of slice by slice excitations, right, to acquire the whole volume. And you can even put the gaps in between the slices so that you can deliver a TMS pulse between the slices. So that's more technically challenging. This is easier, not easy, but easy. So what we start out doing with this is saying, well, you have these resting state networks, right? They're all just a bunch of correlations. We don't really know how well these things are connected. Are they relevant to TMS? If you were to say, stimulate one of the nodes. So TMS usually you apply to one spot, right? So if you stimulate one of these nodes of the network, can you engage the distributed network from doing that? Is that possible? And also there's some evidence of things like antagonism in the networks, task positive versus default mode networks, right? There's this presumed antagonism between them. So you can test those things more definitively and causally with TMS fMRI, which is what we sought to do. Say, can you engage the network when you ping one of these canonical networks? And we found evidence that you can. And you can engage it acutely in response to a TMS pulse. And we also showed evidence that the antagonism is causal. It's not just a correlation that one goes up and the other one goes down. If you engage a task positive network, you get a nice blip of the default mode turning off. Since arriving at Penn, we focused more on some of the deeper brain areas that you cannot reach directly with TMS. And so people are saying, you shouldn't do TMS if you want to reach like the amygdala or the subgenual cingulate or hippocampus, because TMS is to the cortex. It doesn't reach very deep, so you shouldn't bother. But they're skipping over the part where all of these deeper brain areas that are implicated in these disorders also have correlated partners, a putative network partner that is on the cortex that is accessible to TMS. So what would happen if we looked at one of those connected partners on the surface and we stimulated it with the intention then we would reach somewhere like the subgenual cingulate, which is exactly what folks are hoping for when they stimulate like some of the anti-correlated subgenual spots. The assumption is that's the pathway down to the subgenual. We think that that's mechanistically important, so that's what we should stimulate. But TMS fMRI allows us more causal evidence then when you stimulate, you do affect the deeper brain areas that are not directly accessible with TMS in surface. So that's what we set out to do. And so these little blue lines just show where the images are acquired relative to when the single pulses of TMS happen. So it's this interleaved design with the gaps. We stimulate a cortical zone that's guided by resting connectivity. And then what you generate from this is a whole brain map. Now, this looks like any typical fMRI map that you've seen a million times, but this is very different because it's in response to the single pulses, right? So this is a causal map of what's connected to this DLPFC all the way downstream within the constraints of fMRI, being able to localize with its time constraints, et cetera. So these are the downstream partners caused by stimulation to this DLPFC.
Can I ask a quick question? So,
Sure.
So that's not neuromodulation. That's still like individual
Yes,
things.
that's
And
right.
so how come there's multiple individual stimulations?
The reason why we do that is because the same reason why task fMRI is not a single trial, right? You do many of the trials and you assume that any noise that can happen over one trial is going to be mitigated by having more samples of the same fMRI event. So that's what we do. And there is a paper actually. So TMS fMRI is still fairly new, but there is a paper from Colin Hocko in trial showing that you need about 50 events for the single pulse to get a reliable evoked response in the brain. And so we exceed that, we get about 70 stimulations.
What is the typical frequency at which you are actually stimulating? And are you concerned that possibly doing that will actually corrupt the results themselves because you may be actually engaging in neuromodulation without intending to do so?
Yeah, so we only do 70 pulses and we spread them out in these kind of blocks of 10, and it takes about 7 minutes to acquire. And it doesn't look like we're changing the evoked response over the course of that run. So it's not intended to be RTMS. And it doesn't follow a consistent pattern either of stimulation. So the single pulses, they have kind of these mini blocks of 7 stimulations, but we have these catch trials that are kind of interleaved with that. So 1 to 3 catch trials per 10 stimulation block, so that there isn't a reliable pattern. There's gaps between the blocks, and it makes it harder for the participant to anticipate when exactly the TMS is happening. You can kind of hear the volumes being acquired. It's kind of the scanner makes a noise. It goes quiet and then you get a pop, right? So we don't want them to know exactly when the pop is. So in terms of flexibility in image-guided TMS, like we have the neuronavigation software, which is really useful. You can pull up the person's brain imaging data, have them sitting in front of a camera, and you can track where your TMS coil is, where the person's head is, and you can move your TMS coil and see anything from the imaging data that you think could be an interesting target for whatever behavior or symptom you care about, and maintain your coil position with feedback from the camera online. And so it gives you some flexibility in deciding like what's a reasonable way to make an individualized target. Anything that you think, like you can do ASL, DTI, fMRI, task, whatever, and put that into the imaging space and test out a hypothesis about how that circuit works by doing TMS to that particular node of your network. So this one is a replication of a study that, again, Ben was involved in, the first one. So we did a very small study, and now we've replicated our effects from that. Both of those showed that our image-guided, fMRI-guided TMS showed an evoked response in subgenual cingulate and amygdala targets, and then we tried it again in a larger cohort. So one of the One of the criticisms of fMRI is that it's hard to replicate, right? So we, at least in our hands, we've been able to show this consistency that you follow the fMRI guidance and you can replicate your evoked response in the deeper brain target. So that's what we found. In this case, we stimulated in healthy controls. We did the fMRI guided based on positive functional connectivity to the subgenual cingulate. I'll talk more about that, and contrasted that with a control site, which in this case was primary motor cortex, and showed that the fMRI guided gives you a stronger evoked response in the subgenual cingulate. So it does matter where you hold the TMS coil in terms of what evoked response in the brain you get. So as many of you probably are aware, most of the clinical TMS people in depression are looking at subgenual anti-correlated spots. So this is based on resting fMRI. When the subgenual goes up, they're looking for a region at the cortical surface that the activity goes down. So they're anti-correlated over time. That's what most people are focused on clinically. And we thought, why does it have to be positive or anti-correlated? What happens if you stimulate a positive connectivity target? Like, does it make any difference as long as you're hitting subgenual hotspots? So we thought that would be interesting to test out with TMS fMRI. So we did that in our typical interleave design with the single pulses and averaged them to see what would happen. So again, this is a replication of the smaller healthy cohort, this time in 78 healthy controls. And this is the subgenual evoked response following fMRI guided to either the positive connectivity or the anti-correlated target. And in the healthy controls, it didn't seem to matter. As long as you had a high functional connectivity zone, as long as you stimulated high FC, you get a nice evoked response in subgenual. And it doesn't, and they're both negative. So positive FC, negative FC gives you a nice negative bold response in subgenual. When we did this in patients, though, it looked a little bit different. So the anti-correlated is in blue. And you can see it hovers close to zero, but it's not zero. It's still a negative evoked response. So assuming that we want to, with TMS, engage a circuit that goes to the subgenual, and you want to evoke the response, and that's what's mechanistically important for treating depression through this circuit, anti-correlated should work because it still engages the circuit. The interesting difference, though, is that the positive functional connectivity zone evoked a stronger response in the subgenual. So if it is the case that we really want to aim for the subgenual, and that's our priority in depression treatment with TMS, positive connectivity should work even better.
No, the first image where you showed the blue and the yellow, a lot of the dots were actually overlapping or really like intertwined. Is that when we talked earlier about targeting, is that what you mean? Like you try to have them as homogeneous as possible and as separate as possible, like in the other applications?
So they're at least a couple of centimeters apart if you look at the individual subjects data, but then when you average it all together, there's lots of overlap. So that's another piece of evidence to support that things at the group level, when you take them to the individual level, there's some mismatch, and it could actually be important because if I just pick the center of that cloud, right, it might be very close to the center of the cloud for negative and positive connectivity. So you might think, oh, they're at the same place anyway. But on the individual, the native space functional connectivity, there are clear differences, and we could always find them. We would always find clear homogeneous zones of positive connectivity and anti-correlated. So you can absolutely find them on every patient, and you can stimulate at the cortex.
And have you ever tried to look at absolute connectivity? Like, because pooling positive and negative might give you slightly different regions that have strongest absolute rather than, separate them out.
Yeah, we did that in the smaller pilot, and since they were healthies, again, it's the absolute value is totally reasonable, and as long as you have a high connectivity, negative or positive, it gives you a nice subgenual effect. So the only place where we saw the difference by that valence was in the depressed patients.
Really interesting data on the positive and negative correlation. Do you have any data on the effect of repetitive stimulation pulse trains at the positive side?
Have clinical evidence, and we have so we will absolutely circle back to that, but the RTMS effect on the subgenual when we did a fairly weak short round didn't acutely change the evoked response in subgenual. So but we did some interventions that I think are meaningful to that circuit. So before we switch to the repetitive TMS stuff, here's our other pathway, which again is a replication of the smaller cohort in healthy controls. And we're looking for an evoked response based on functional connectivity, positive FC to the ventrolateral prefrontal cortex, and aiming for the amygdala, high connectivity with the amygdala. And we found evidence that we could evoke a strong amygdala evoked response. We also collected DTI, which we did not use for targeting, but we looked at it post hoc and did tractography between where we stimulated in the VLPFC and the amygdala with the hypothesis that TMS likes to propagate along white matter pathways. And so if there's this direct connection suggested by monkey tracing studies, which is why we chose this general region of cortex, then TMS should propagate through that pathway, that direct pathway, and there might even be a relationship between the strength of the evoked response in the amygdala and the integrity of that pathway, which is what we found. So suggesting that if an individual patient has particularly strong connections structurally between where you're stimulating and your subcortical target, then the subcortical target is going to be especially effectively engaged. So these are neat tricks. You make these little brain blips happen in response to these single pulses of TMS, but is there any clinical relevance if you do RTMS to these evoked brain responses? So let me explain what we did and why we did that. We're like, okay, you could do a full clinical trial, right? You could do like 4 to 6 weeks of daily RTMS to a new pathway that I think might be clinically interesting, right? And that's a big burden for the patients with this unknown pathway. That's a big burden for us as people who provide the stimulation. So are there any shortcuts? Can we take a shortcut? What if we only did like a few days of RTMS to one of these pathways, and we do it a sufficient dose that we think that's enough to move symptoms, and we want to capture a brain response. We want to do TMS fMRI and link it to a clinical response. Can we get away with that? Can we just do a few days worth and ping it, and then ping it again afterwards and capture something interesting? So we set out to try that. With the priority that we're not in this case trying to show the maximum clinical efficacy of this new target. Instead, we're trying to show that there's a reasonable clinical change that we can link to the circuit engagement and modulation that we're going to test with TMS. And also, we're going to make these whole brain maps. I mean, these are new things. We can show what's connected to those brain regions downstream in this new way that correlational imaging can't actually do. And so we have this one short protocol. We have one pathway that we're choosing to link the TMS fMRI to a clinical effect. So it's not sham controlled. This is not the maximum clinical benefit through this pathway. We're just trying to link these measurements, TMS fMRI, this circuit. And if it doesn't work, right, we can say, oh, that's because we're hitting a positive connectivity target. We could just switch and hit the anti-correlated spot, do another 3 days, hit another target that you think is meaningful. So the general framework is that let's figure out a way to iterate through these potential targets faster before we bring in hundreds of patients and stimulate them over many sessions. So that was the hope. And so this is our imaging protocol. We collect a baseline scan, structural and resting connectivity, so that we can determine an individualized target for every patient. We bring them back and do this interleave TMS fMRI stuff to ping the circuit and see how it's connected. Then we do these 3 days of RTMS outside of the scanner with intermittent data burst, and then we ping the circuit again to see if there's any changes. So this is what it looks like when somebody's outside of the scanner getting their TMS. And so in this case, we did intermittent data burst through that putative subgenual pathway with 2,400 pulses per day, 3 days. What we found is that if you look at the pre-intervention TMS fMRI, so the evoked response to the single pulses to the subgenual, we have this nice subgenual evoked response, and the degree to which that subgenual response is evoked in the individual patient predicts how well they're going to improve with the TMS through that circuit. So this is the first evidence that we engage a circuit. You can do that before the intervention, and you can say something meaningful clinically about the patient's likelihood to respond. Supporting TMS fMRI, thank goodness that we found that, otherwise we'd have to scrap everything. But then we pinged the circuit again after the intervention, and we found again this association, this time between the change in the evoked response in the subgenual, which we're aiming for, and depression improvement. This is supporting subgenual as a reasonable target for TMS. The symptoms improved about 30%, 32% over these 3 days. That's not terrible. It's only 3 days, but like we could push it even further without the 3 days. But just to show that we had a meaningful clinical change and we linked it to the TMS fMRI, both as a prognostic predictor, circuit integrity pathway, but also as an association with clinical change. So ping it before and ping it after.
So really interesting result. This was 4 sessions in one day?
3 sessions, so 1 session per day for 3 consecutive days.
Each session. Okay. And the spot that you were stimulating at was the positively correlated
That's right.
spot?
Yeah.
So the extent to which you were able to increase the SGACC signal correlated with improved.
Very close. It's actually decreased the subgenual.
Decrease.
Yeah. Yeah.
No, I'm looking at the SGACC increase values. Like if you did like a 95% interval, it probably would hover around 0.
Yeah.
It's like a little more positive, a little more negative, and it's actually something you also see with G. It's it's increased, but really it's around 0. What do you make of that?
Yeah, I think we may not have the ideal stimulation protocol, right, to consistently push the subgenual in a consistent direction. And it may just be because the dose was not strong enough. It gives us some nice variability in the amount of subgenual evoked response change that we can link to the depression improvement, but it leaves us open to pursuing other stimulation protocols that are either at a higher dose or even a different, more effective stimulation protocol than the one that we used.
So you may address this later, but is there any evidence that the hotspot changes after every 3 days? Like it's a dynamic target?
Yeah, it moves. It moves. And so I actually don't show this slide, but so we have resting connectivity that we use to determine the target, right? And that's on average like 2 weeks, almost 2 weeks before we do the intervention. And then we do the TMS fMRI session where we again acquire resting connectivity. So we don't change the target, but we acquire it again like the day before we start the intervention. And only the connectivity from the time point right before the intervention and not the original baseline one predicted depression. So it does move, right? And so if we were to choose a different target based on top connectivity shortly before the TMS session, we might have had even stronger clinical effects because it definitely looks like it's shifting.
So it shifts even without an intervention.
Yes, yeah, just over time.
And then with the intervention, did that shift even more, or is it the type of shifting? Does that change?
That's a good question. We didn't look at the functional connectivity change post intervention, and I'll tell you why we decided to prioritize all of our interpretations around the TMS fMRI signal. So if we take the functional connectivity from the time right before they have the intervention, same day as the TMS fMRI session, you put the connectivity from that day in to the model predicting depression improvement, and you put the TMS evoked change as a predictor. And functional connectivity drops out of the model, no longer significant. TMS fMRI is still significant. So it soaks up the variance of functional connectivity and additionally explains more of the depression improvement. So we're like, all right, TMS fMRI, that's our ticket. That's even better. And there are papers where people in larger samples than ours are suspicious of the connectivity value and whether it's really meaningful for a clinical predictor. Still works for a target. Where do you put the TMS coil? But the actual value of what you get, connectivity, doesn't seem to be in our data as meaningful in predicting the clinical. So I didn't do a sham control, but I did TMS fMRI and amygdala pathway. And I get the whole brain for free. When we do TMS fMRI, look at anywhere else in the brain you want to. So what we did is said, okay, well, we have our SJCC pathway. We get an evoked response in the SJCC. We can take the amygdala pathway, see what happens in the evoked response to subgenual. We can take the subgenual connectivity and look at a different spot like the amygdala and see its evoked response and do that again with the amygdala FC target, right? So circuit specificity. We're looking for evidence supporting that it's only this blue line where we think the connectivity is high to subgenual, where we did the intervention, and the downstream target that we thought was the one that we were chasing to improve depression. And we found evidence that only that dark blue pathway is the one associated with depression improvement, none of the others. So suggesting there's some specificity in our targeting, in our outcomes, and linking more tightly the subgenual evoked response to depression improvement. I'll also say anxiety also improved. Like, okay, anxiety also improves, but does it have anything to do with the subgenual? So it could be the case. It's not like there's a wire between the TMS coil and the subgenual that passes through nothing else gets engaged, and we're only stimulating the subgenual, right? Even with deep brain stimulation, you put an electrode in a spot and you're changing communication patterns. It's not like this brain exists in a petri dish and you're only affecting that region. So we had this nice DAS-21, which separates out the depression, mood-related kind of stuff from a certain flavor of anxiety, which is like arousal, hypervigilance kind of stuff in anxiety. And we found that even though both of them improved, the subgenual evoked response and its change was related to the depression improvement, but not associated with the anxiety improvement. So even though we get the anxiety improving, it doesn't seem to be connected to what happened in the subgenual. So you might ask, well, how did anxiety improve then? Since we have these new maps, right, these unprecedented maps of this causal connections between stimulation sites and downstream regions, and we're not relying on functional connectivity or these correlations, what can we tell from the causal maps, the degree to which they changed and depression improvement and anxiety? And so like if the subgenual is working within a network, there should be other regions that also come online, that if you look at other places in the brain, that it won't only be the subgenual that's changing associated with the depression improvement. And indeed, we found that the subgenual pops up as a hotspot. So that's lucky. We were aiming for that. And that's one of the hotspots showing the association with the evoked response change. But there are other regions, posterior cingulate, hippocampus, that also, when they're changing, depression is improving. So it's definitely not a single region, it's a network, but that region stands out as particularly important. Whereas flip it over to anxiety, and there's actually an amygdala association with anxiety improvement. There's also a nearby region of ventromedial prefrontal cortex that if you engage and modulate that region, you improve anxiety. So if you're using these as a new causal map for deciding a potential new pathway or treating this flavor of anxiety, you might use these regions as seeds, find functional connectivity on the individual patients, and try stimulating those pathways.
Can I ask you what the unit of the color is? I'm wondering because I feel like the effect sizes, if we can speak of it in that term, is like tenfold for the anxiety
Yeah,
versus the depression.
yeah. It's not a straight up fMRI. It's like a beta weight association. Yeah.
I see.
So we do get some really strong associations with anxiety. I would consider both of these maps exploratory. These are not the regions that we're aiming for.
Yeah.
And so just casting the whole brain data out into the world to generate hypotheses, I'm not assuming that we know what regions to stimulate prospectively for treating these symptoms separately. But this is a new map, and we may try it. Another thing is that when we recruit patients for our studies, we don't limit it to treatment-resistant depression. That's an insurance kind of issue. That insurance will cover it if you don't respond to antidepressants. But just by chance, we get a fair number of treatment-resistant patients because they're looking for alternative treatments in the community, and they come across this, right? So if we split out the patient data for the treatment-resistant in blue versus the non-treatment resistant, the TRD patients have baseline symptoms that are higher, as you might expect, but both groups respond equally well to TMS through this pathway. So it's not like we found the treatment-resistant depression stimulation pathway. We think this is a broader depression treatment pathway. And in support of the idea that maybe more patients could be benefiting from TMS, which probably is not hard to sell on you guys, but there's this new paper where they're on their first line antidepressant, and then some of the patients either had augmentation or switched to venlafaxine, and this supports the switch to TMS rather than to a different medication if the patients aren't initially responding. So maybe we could, capture a larger number of patients and reduce the threshold for determining which patients might benefit from a course of TMS. Preliminary, right? Not long-term evidence, et cetera. But let's also look into, we did a clinical trial without TMS fMRI because that's what the budget would allow. And we did functional connectivity, positive connectivity to a mixed group of PTSD and depression. Those conditions are highly comorbid. There's no FDA-approved TMS for PTSD, so worth exploring. So we did this clinical trial in 45 patients who had diagnosis of PTSD and depression. We wanted to contrast our fMRI-guided precision mapped target with a scalp-based target, 6 centimeters anterior to motor cortex. The reason why this was one of the many reasons why this was a shot in the dark and might not have worked is because the scalp target, just by chance, right? Some of your patients, you're not looking at their imaging data. And so just by chance, you're still in DLPFC. Some of those people are going to have connectivity, a reasonable amount of connectivity with your target if you're not looking at their imaging data, you're just using the scalp. So there's going to be some overlap. And that means it's going to be even harder to prove that image-guided beats the scalp-based target, especially in a fairly small clinical trial. But it's amazing for those of us who are really into imaging. It's kind of amazing that there's no positive evidence in the literature already showing that fMRI-guided beats a structural target or a scalp-based target. And that's really important if we want to really sell the utility of this precision mapping sort of approach in treating patients. So we did this. This is what their TMS sessions looked like. They had 1,200 pulses of intermittent data bursts, either to the fMRI guided or the scalp 6 centimeter target. We did this other crazy thing where we had them do a task in between 2 rounds each day, and they were randomized to either get this in-back working memory, which was supposed to be like a higher arousal, engagement, attention grabbing task, versus this relaxing nature video. And we asked the patients how they responded to those, and it's pretty consistent that, you know, they got more tense with the working memory task and they relaxed more with the video. And we thought, you know, that's an easy manipulation. You could do this in any clinic. It doesn't cost you anything. You can have somebody do a task in conjunction with their TMS and see if it interacts with the target and improves outcome. But aside from the task, like our real kind of top priority was to show that fMRI guided might beat the scalp-based target. So this is the 6 centimeter target is in blue, it's already stimulated, and then the fMRI guided is in red. So like I said before, there's just by chance, there's going to be some of these blue targets that like are pretty close to a high connectivity zone for a patient. So it's going to be pretty hard to establish on average that the fMRI guided target is better. We're in the same region of the brain, and you're just targeting slightly differently based on the scalp or fMRI. This is what the clinical effects look like over time from the 2 weeks out to longer term follow-up. And the purple is the fMRI guided. The gray is the scalp. So the top left is the PTSD checklist. So that's the overall PTSD severity. And you can see like purple and gray following it over time, the patients get better, which is good, but they stay pretty consistent neck and neck, even in the longer term follow-up, that the clinical effects are pretty similar for the scalp-based and fMRI guided. Now the top right is the PHQ-9, so the depression symptoms, and you can see from like 4 weeks out, so they get the treatment for 2 weeks, right? And at the 4-week period, you can already see that the fMRI guided is really doing much better, and that consistently sticks around through to the follow-up period where the fMRI guided treats the patients better. And these are symptom change scores. So the fMRI guided gets you about 60% improvement, and the scalp-based target gets you about 50% improvement. So hopefully a meaningful difference in people's lives and, you know, important functional outcomes, but still I want to figure that out. And then, so that I would consider this exploratory. We pulled apart the PCL subscales, and only one of them showed a difference between fMRI guided and scalp target, and that was the hyperarousal subscale on the PTSD checklist, where the image guided did a better job at helping with that particular symptom. And there was no symptom subscale or time point where the scalp target beat the fMRI guided. So either they're equivalent or the fMRI guided wins across the board when you're looking at the subscales and you've got 2 different symptom categories.
Any particular reason you chose 6 centimeter rather than just F3?
No, we could easily run this study with F3. It's another totally reasonable target. So yeah, we were just looking for something that was that we thought was going to be relatively close to where we would stimulate with the FMI guided, and thought that, yeah, that's we consistently see hotspots. And if we can beat the scalp target that is right in really close proximity to the 6 centimeter target, then that would be a big win.
And this is all using the fMRI kind of targeting. So between the two groups, I'm assuming the coil stayed on target on average, same between the two groups.
Absolutely, we have precise feedback online throughout the whole TMS session. So we're neuronavigating. We never turn that off. We draw a big X on the target, and we maintain the coil position all the time. So they're done exactly the same way. From the patient's perspective, like both of the targets are in the navigation software, right? So they don't see the fMRI underlay either. Well, I wipe that out before I give it to the technician to do the stimulation. So you can't see that there's a blob there that sometimes you're holding outward or sometimes you're not. So they just know it's target A, target B, and they're getting stimulated with one of the other.
Excuse me, I noticed that on the total PCL, there seems to be a trend for after week 8 for the measure, the 6 centimeter guided to be better than the image guided, whereas you said that none of the subscales showed any advantage for the 6 centimeter guided. I'm just wondering, and I'm wondering, oh, there we go. Okay. I'm wondering about the
Here's the post treatment.
Repeat the question.
Sure.
go back to the previous
About
one.
whether there is maybe a particular time point or something where the scalp-based target looks like it might have been slightly better. But here's another way of representing the data where you can see the error bars crossing 0. So there was some like substantial variability, I would say, in the PCL response, where on average it was slightly weighed towards the fMRI guided, but yeah, especially if you pick out some of those individual time points along the way, there are moments where you have a trend suggesting the scalp. But in this small sample, I wouldn't trust that at all, and but it's worth following up. And I'll also say that I kind of skipped over the interaction with the task, but there was an interaction with task and target on one of the PCL subscales. So this was not predicted. This is something that I don't have much confidence in, but I do think it's sort of suggestive that there may be an interaction between which target you choose and what scalp or what the task and target interaction. I think that there's probably some real meaning behind that, and it would be fun to test out. Again, easy to manipulate. We know what targets we're stimulating in your guys' clinic. Like, throw a task in there, see if it makes any difference with the F3 target or with another one that you guys are stimulating to see if it contributes to the outcome. So it'd be like treatment as usual with a small little consent form where they're like, yeah, I'll do that task, and you just add that on, and you might have some really low cost way of boosting the clinical outcomes potentially. Right, this is early days, but something that we can easily manipulate. I also want to say that image guidance isn't always best. The BMF3 is pretty good, right? And this is a much larger study than what we ran, running connectivity guided targets to a totally different target. This one still in left DLPFC, right? But this time based on right anterior insula connectivity. So they had some like biomarker evidence from a prior study, and they thought this one might be interesting. But look at this, they ran this huge study with this enormous amount of patients, and they had to run imaging on all these people, like a full clinical trial, and it didn't beat F3. It's like, oh man, maybe we could have figured this out if we did one of those brief intervention protocols over 3 days and see if it changes the circuit. But it also supports the idea that it's not DLPFC, even left DLPFC is not all just one thing, and any fMRI signal from that zone isn't going to give you a better clinical outcome. It's really important, like what actual target you choose and where you place that TMS coil. If we want to beat the F3, which is also already decent, then we have to show, like, we have to really use a better target than what's already there.
Well, could it
I
be
also
that
mentioned,
with the full protocol, all the patients got better in both groups, or, you know, the asymptotic number of patients got better in both groups, so it's a ceiling effect.
Yes, the patients got better. I also say that there's differences in dose across these studies that may be relevant. So this study that I'm showing you had 60,000 stimulations. That's a pretty high number historically. The same protocol from Stanford has 90,000. Mine only had 24,000. I also want to mention that that you could have a hypothesis about which node of a network really is going to engage the circuit well, and it's within our ability to stimulate multiple potential pathways to engage that network with that individual patient before you ever treat them through that target. Show a differential engagement according to that spot and plan that that's where you should stimulate to affect the patient's symptoms the best. That's expensive, but it's potentially clinically useful. I'm going to skip through these fairly quickly. I'll just say we're not the only ones that shows like circuit engagement from stimulation. This is one with DBS fMRI, which is another super challenging thing, showing that engagement of stimulate subgenual, show engagement of dorsal cingulate related to clinical improvement with DBS patients. Also symptom-specific stuff, we're not the only ones chasing that target. This was a really nice paper that I think a lot of you probably know about, suggesting this is based on a big normative cohort of connectivity and to parcelate the network, saying that, hey, if you stimulate in this network, you might get more leverage on dysphoria versus anxiosomatic symptoms. So definitely different approaches to targeting stimulation and symptom-specific targets. Yeah, and there's more of that with like DTI, neurological disease, and OCD, and another kind of approach is that maybe we need to make fMRI more sensitive. It's hard to find a biomarker because people are just laying there at rest, and maybe if you do something that's more relevant to their symptoms, then you'll capture a more meaningful fMRI target. So this is our beginning attempts at that. We have people do depressive rumination and worry in the scanner. We kind of train them how to do it. We allow them to opt out of it so that we get high confidence in these chunks of fMRI that we believe they're in the zone of doing the task, which we think is important. So we're working on TMSing those spots. So I should try to wrap this up soon. We think that fMRI guided targeting works. According to these NLE TMS fMRI, we can reach some of these deeper subcortical targets. That engagement also is not just like a fun parlor trick. We think it's relevant to clinical effects of RTMS. And at least in some cases, fMRI-guided TMS is more clinically effective. And so adding imaging to brain stimulation protocols is super useful, especially when you have something that works, to figure out why some patients don't respond and plan the next round of even more precise targeting. Anybody's interested in doing the task, we have this HIPAA compliant red cap feeding task, easy to do on a tablet that you can do in your clinic. We're planning on getting a controllable TMS system that we're going to focus on motor cortex. You guys happen to have one of those sitting around gathering dust, we'd love to collaborate with you. And also funders and my great center and collaborators at Penn.
Any questions? Anyone?
Do you know which subnuclei of the amygdala the VLPFC connected to? And from the image, it looked like it was on the left. Sorry, am I coming through?
Did you hear what he asked?
Can you speak louder?
I can. Maybe there's something
I have a sound issue.
on my side.
The
Um,
sound is at 100.
Yeah. I asked if there's the subnuclei of the amygdala targeted by ventrolateral.
Ah, yeah, that's a great question. I will say that we don't have very good evidence that the subnuclei are differently engaged. So if you look at the peak evoked response in the subgenual, it covers the three major subdivisions of the amygdala that you get from the Ulic atlas. So the specificity within the amygdala does not appear to be great at the moment.
Thank you.
Sure.
I have a quick question. Do you get motion artifacts? So it's like TMS, scanner, and what do you do? Like,
Yeah, head motion is a terrible confound in all of functional MRI, and so the one of the really advantageous aspects of fMRI with a gap for the TMS is that if there's a little shudder of the head movement in response to those single pulses, you don't capture that if you have the gap. So if you have a brief shudder and their scalp goes right back against the coil, which you hope, and then you acquire your image from it. So our head motion, when we look at the imaging data, is very, very low, but I still assume that there's a little bump. So there's a little bit of like wiggle of the TMS coil itself, of the scalp muscle, like wiggling the TMS coil a little bit, like a little shake, right, through the whole system that really would mess up our imaging data if we didn't have the gaps. But we train the people also to keep really still, and we give them test pulses at the spots before we send them into the scanner, so that there's often this like big startle response when they get their first couple of pulses to that new location, and then they're generally able to stay very still for us.
yeah, that makes sense. I think as long as the head motion blocks, like you said, don't show too much motion, then it should help.
In the early days, we would stop a scan when we saw the head motion, scold the participants, and remind them to keep their heads still. So we do online reconstruction of the images, so we can see the trace of the head motion over time, and we will stop the scan and we'll punish them with more TMS if they could move too much. But participants, with those extra steps that we take to make sure that they're not too surprised, it works very well.
And I guess the concurrent system, like, are there blind spots, or are there locations that one would not be able to administer the TMS to? And the context is, I think you showed a paper from the Boston group, Sean Siddiqui. So they were suggesting for depression an orbital frontal target of their review paper. So I just wonder whether and the concurrent single pulse TMS fMRI be used to test all targets, or do we?
There are absolutely limitations to where you can position the coil, and we have a custom build a coil holder that gets us into more positions than the commercial one. But also say that if you don't need the participant to look at a screen and see something for a task, you have a lot more flexibility with where they position their heads. But if they position them way off of center, you might have to acquire an structural image to make sure that you can normalize their scan. But we can get pretty far back. We've hit M1 and TPJ. There's a guy also in Boston who has people lay prone, so face down, and can stimulate the cerebellum. So you can do a lot, especially if you don't care whether they can see anything.
Yeah. Thank you.
You know, if you're doing e-field modeling, they kind of promise you to see activation right at the stimulation site,
Yeah.
which you never do with the concurrent TMS MRI. I do know that you see, network effects spread out here and there, but what do you make of that? Like, how do you explain it? Do you think it's just the nature of the dose signal versus electrophysiological signal, or?
Yeah, I think there are probably a few factors contributing to making it really hard to get a good signal under the TMS coil. There is a protocol, though, that's run by guys in Austria who have a surface receiver coil placed directly on the scalp with a TMS coil attached to it, and they run bursts of RTMS, and they get beautiful cytostimulation right under the TMS coil. Right. In most other occasions, we don't get a really nice one. There's like a little bit of dropout from the equipment. There's some eddy current. There's like even if you put electrodes down and try to capture individual like clusters of cells responding to single pulses, the depth of that of the spikes, how far away the spikes are happening is like 2 millimeters, and it's a minority of the cells responding to that. Obviously, like you get communication through that circuit. You can make somebody's finger jump really reliably, and you get clinical effects, but the cytostimulation is just really elusive, and we've been testing different protocols trying to capture it better. We've been using this like low resolution quad coil because it fits the TMS coil, right? But there is a more expensive one that's an 8-channel coil that we just bought, and we're going to start testing with that and see if we can maybe capture some of that response. But the general consensus in the field is that it's very hard to get.
Do you really think it's the geometrical properties of the receiver and how you capture the signal really more than physiological? It seems like you haven't given up on
we'll keep playing around with it because it would be really useful to find the response right there, especially when you don't, if you care more about surface level network kind of engagement rather than the deeper brain areas.
And then I have a question. So for your amygdala targeting study, you mentioned that the VLPFC targets, which were both negatively or positively correlated with the amygdala, engaged the target. I was wondering if you used the directionality of that initial functional connectivity as a variable in any of your downstream analyses, or did it influence your decision making at any point?
Yeah, we followed the positive connectivity for the replication study, and so it doesn't seem like it makes any difference. Like it really looks like the absolute value of the connectivity for that amygdala target is, gives you a reasonable place to put the TMS coil. But again, putting these caveats around functional connectivity and what the values mean with respect to TMS effects in the brain, that connection is not super solid. And then you do something like as far removed from that as an intervention study, trying to link those. I think it's not particularly surprising that the actual connectivity values don't line up super well that way.
Thank you.
Do you have any thoughts on technology outside of fMRI? For example, like low signal from near infrared?
Yeah, there are some promising studies. So Jing Jiang in Iowa is doing FNIRS focused TMS. That's a main imaging outcome. I think with all imaging, there are benefits and there are shortcomings of applying TMS to it. Like EEG is clearly easier to accomplish and cheaper and can go to more places, but there's some significant barriers to getting an evoked EEG response to TMS. Lots of sources of noise. I'm going to capture something that's pretty quick, right? So there's a lot mechanically, signal-wise, physiologically, sensory-wise that you have to try to clean up to get a good brain response.
And I would imagine we can't really capture the deeper brain structures.
Yes, right. Yeah. That's I would say you can't. Saying can't may be too strong of a word. I would say it's challenging to interpret the source of the EEG signals in many cases.